Hi, I'm Rajib Bhomik and I welcome you to my own YouTube channel. Today we will discuss about coordination compounds. So this is a very important part of our inorganic chemistry in class 12 and question also come in NEET and JE also. So I think this is a good chapter to discuss. So we start our class here. Now we can see in the screen that generally salts are of five types. Generally, salts are of five types. One is the normal salt, second one is the acidic salt, third one is the basic salt, fourth is the dye salt or double salt, or fifth is the complex salt. So in class 9 and 10 we studied these salts, but in class 12 we will study complex salt. So at first, before starting, we should talk about dye salts. This is also very important. So disalts or double salts. I have given an example here, that is K2SO4 dot Al2SO4 whole 3 dot 24 H2O. As we know, this is known as alum or potash alum. Potash alum means generally it is a disalt. Or we can write down another example, that is ammon alum. This is another example of disalt. So disalts, we should start with the definition first. Disalts are the substances which gets completely dissociated into their component ions in aqueous solutions. As an example, this is a disalt, potassium. When you give water into it, this will give K plus, Al plus 3 and SO4 2 minus. They are the component ions present in the compound, in the salt. You can see there is specific reason that we call this an alarm. We should know also this no. Now see, in case of alarm, one cation should be in the plus 1 oxidation state, another cation should be in the plus 3 oxidation state, and there should be 24 H2O or 24 molecules of water that should be present for the water of crystallization, that should be present as the water of crystallization. So this is also an alarm because ammonium has a plus 1 oxidation state, aluminum has a plus 3 oxidation state, and there are 24 molecules of water which are present as the water of crystallization uh, to give this a geometrical shape. So now you can see another example of disalt, that is carnallite KCl.MgCl2.6H2O. This is used as a major ore of potassium and magnesium. So whenever you give H2O in carnallite, this will break into K plus, Cl minus and Mg2 plus. But how can we know that this has been broken into K plus, Cl minus and Mg2 plus? So we have to do the salt analysis for this compound. Now, for potassium as an example, uh, if we add sodium cobalt nitrate in the aqueous solution of this salt, we will get this will give a yellow precipitate of potassium cobalt nitrate. Similarly, for chloride ion test, we can do such as in the aqueous solution. In the aqueous solution of the salt, we will add some amount of HNO3 to acidify the solution. Then we should add AgNO3. Then a precipitate of AgCl that is white in cardi white in color uh, should appear. Now, this does not mean that the chloride ion test is confirmed. This chloride ion should be further confirmed by the addition of ammonium hydroxide. Whenever you give ammonium hydroxide in the white precipitate, the precipitate will dissolve. This will form a complex which is known as diamine silver 1 chloride. Okay, this is a separate issue. Now, why the precipitate appears with the help of HNO3? Now you should see that HNO3 has NO3 minus ion and AgNO3 has also NO3 minus ion. Due to the common ion effect of the nitrate ion, the precipitation of AgCl appears in this case. In case of similarly, we can do the test for magnesium 2 plus also. So what we have done here, we have seen that Salts are of 5 types: normal salt, acidic salt, basic salt, dye salt, and complex salt. Dye salt is also called a double salt. As an example of double salt, we can see K2SO4.L2SO4 whole 3.24H2, that is the alum, or it is also called potash alum. M1 alum NH4 whole 2SO4.L2SO4 whole 3.24H2O. There is a specific reason that we can call them alum, because the cation, one cation present in potash alum, that is the K plus in the +1 oxidation state, and aluminum in the +3 oxidation state. Sulfate is SO4 2 minus. There are 24 H2O present in the molecule for the crystal structure. So this is a special property of alum. Now this is also a disalt, but this is not an alum. Okay. So all the disalts are not alums, but all the alums are disalts. So with this, we conclude the disalt. Now, I'm going to the complex salt. Complex salt, as an example of complex salt, I have written an example K4FeCN whole 6. This is known as potassium ferrocyanide, or it is it is a pet name. IPC is potassium hexacyanoferrate. Now, in case of complex salt, there are two parts. Complex, we first go through the definition of complex salts. Complex are the substances which can retain their identity in the aqueous solution as well as in the solid state. Complex salts, now you can see here, this is K4FeCN whole 6, potassium ferrocyanide. Whenever we give H2O or dissolve it, this will give 4K plus and FeCN whole 6 4 minus. Now you can see that this part of the complex salt has retained its integrity or identity in the solid state as well as in the solution. Now you can see there are two parts. The two parts, that is the part present in the third bracket, this is known as the coordination sphere, and the part which is present outside of the bracket, this is known as the ionization sphere. Coordination sphere and ionization sphere. Actually, this ionization sphere is not an integrated part of the complex. This is here present due to the charge balance. We will see the next thing. Now see, this is the coordination sphere that remains intact in the solid state as well as in the solution. Now, see, a complex compound has three parts generally. One is the counter ion, that is the ionization sphere. Another is the central metal atom, and the rest of the part is known as the ligands or ligands. So potassium is known as the counter ion, iron is known as the central metal atom, and cyanide is called as the ligand. Now see, central metal atom. Central metal atom, these are Lewis acids, because if we go through the definition of the central metal atom, we will find out why this is Lewis acid. They can accept one or more than one pair of electron. Now see, according to the definition of Lewis acids, we know that the substances that can accommodate a pair or more than a pair of electron are known as the Lewis acids. Now see, the central metal atoms can accept one or more than one pair of electron in them. So they are generally Lewis acids. Generally, the d block elements or the transition elements behaves as the central metal atoms, such as titanium, vanadium, chromium, manganese, iron, cobalt, copper, etc., ruthenium, osmium, rhenium, silver, gold, and we can also see many other elements which can behave as the show complexes. As an example, ruthenium red is a complex that is used in some Mughal empires, and also Mughal blue is also used in Taj Mahals and different places in the Mughal empire. So central metal atom, metal atoms are the Lewis acids. They can accept one or more than one pair of electron. So they are the Lewis acids. So the counterpart, that is the ligands. Ligands are the Lewis bases. We can see from the definition, they can donate a pair or more than a pair of electron. They can donate a pair or more than a pair of electron. That means, according to the Lewis acid base theory, we know that the substances which can donate a pair of electron or more than a pair of electron is known as Lewis base. So ligands are the Lewis bases. The most important part of ligands, that is the classification of the ligands. very important classification is present here. Now, classification can be done in various ways. So depending upon the denticity, the classification is done. Denticity means, you can see by the definition, how many number of donor atoms are present in the ligand. Now it is very easy. Now see monodentate. Monodentate means, mono means one, dentate means number of donor atoms. Okay? Number of donor atoms. So monodentate means having only one donor atom. Monodentate means having only one donor atom. Now see, as an example, this is the fluoride ion, chloride ion, bromide ion, iodine, iodide ion. So there are two other examples, H2O and ammonia. So monodentate ligand means having only one donor atom. Some of the students may have the confusion that in case of H2O and NH3, how this is a monodentate ligand. Now we should draw the structure of the ammonia. So now NH3 and H3 is a pyramidal structure. So lone pair is present in the apical position. So you should see from here that the definition is having how many number of donor atoms, that is the denticity, having only one donor atom. Now see, it is a tetraatomic molecule, but this is none of my business. My business is number of carrying, number of lone pair containing or carrying atom. This is the number, and this is the lone pair carrying atom, that is in number one. So that is monodentate ligand. In case of H2O, you should see there are two lone pairs present in oxygen atom, but this is none of my business. Number of atoms that are carrying the lone pairs is one. So this is also monodentate ligand. Monodentate, this is monodentate. Monodentate means having only one donor atom. Bidentate ligands, two donor atoms. Now see, ethylene diamine. This is a classical example of bidentate ligands. Ethylene diamine, that is NH2 single bond CH2 single bond CH2 single bond NH2. So you should see bidentate ligands, there are two donor atoms. Now you see, here is one nitrogen atom having a lone pair. Here is one nitrogen atom having a lone pair. So this is a bidentate ligand. Name is ethylene diamine. Ethylene diamine, in case of coordination chemistry, this is written in the short form as EN, small e and small n. So this is known as ethylene diamine. Now you should see another example of bidentate ligands, that is oxalato. Oxalato means OX. This is the short form of oxalato. We should see the structure. Oxalato comes from oxalic acid. Oxalic acid, that is COOH, COOH. So if two hydrogen H plus, two protons are liberated from here, so there will be two negative charges. So these two atoms, two oxygen atoms are containing the negative charges. So two donor atoms are present. That's why oxalato is a bidentate ligand. Now see here, bipyridyl. Bipyridyl is also a bidentate ligand. You should see, this is the structure of pyridine. Not actually pyridine, this is pyridyl, because in case of pyridine, here should be a hydrogen atom. But here, the hydrogen atom is replaced or substituted by another group. That's why it is known as pyridyl. So two pyridyl moieties are attached with each other in a conjugated form is known as a bipyridyl, because two number of atoms, two nitrogen atoms having lone pairs. So this is known as bipyridyl. Now we should see another example of uh, bidentate ligands, that is the orthophenanthrolene. So another, some examples are there also, orthopicoline, beta picoline, etc. Polydentate ligands having more than two donor atoms. Having more than two donor atoms. Poly means more than two. Uh, Poly means more than two. Now you should see there are more than two donor atoms in EDTA, ethylene diamine tetraacetate. Now you see, in case of ethylene diamine tetraacetate, if hydrogens are present, that is, it is known as ethylene diamine tetraacetic acid. If hydrogens are liberated, that is known as ethylene diamine tetraacetate. You should see the structure. Here is one nitrogen atom, one donor atom, nitrogen atom, another donor atom. So two. Here 1, 3, 4, 5, 6. So EDTA has 6 donor atoms. That's why it is known as a hexadentate ligand. You should see hexadentate. Hexa means 6, dentate means number of atoms 6. Hexadentate ligands. So hexadentate ligand is a classification. This is a polydentate ligand. It is EDTA, ethylene diamine tetraacetate. Now you should see flexidentate ligand. Flexidentate ligand means the denticity is flexible. In case of EDTA, there are 6 donor atoms, but it can coordinate through its only 5 donor sites also, and can also coordinate through 4 donor sites, then its denticity will become pentadentate and tetradentate. So the denticity is flexible in case of EDTA, so it is a flexidentate ligand. So just to review, okay. Okay. So classification of ligands depending upon the denticity. Denticity means how many number of donor atoms are present. So we go through monodentate ligand. Monodentate ligand means having only one donor atom. That is the F minus, Cl minus, Br minus, I minus. You should remember, higher the electronegativity, lower is the ligand strength, because it will not be able to donate its lone pair, because the electronegativity is high. So it will attract the share, it attract the paired electrons. So it will not donate. So Cl minus, Br minus, I minus, H2O, ammonia, etc. So you should see in case of ammonia, there are 4 atoms which are present in the molecule, but the nitrogen atom, that is the single atom which is containing the lone pair. So that is the monodentate ligand. In case of H2, also one is there, oxygen. So bidentate ligand is ethylene diamine, oxalato containing 2 donor atoms. Bipyridyl is also there, orthophenanthrolene. Flexidentate ligands means the denticity is flexible. Now we are going through a classical example of chelating ligands. Generally, we should know what is chelate. Chelate means cyclic. Chelate means cyclic. So we should see a question comes in the came in the previous year NEET examination. There were four options were there, but I wrote only 2. So K4FeCN 6COEN whole 3 Cl3. In case question comes, which one is more stable? So you should see the chelate is more stable. Chelate, what is chelate? Chelate means you should know naturally occurring bidentate ligand. Now you see here, this is a bidentate ligand. The bidentate ligands can coordinate through both their donor sites, Now you see there is a cycle. As a ring has been produced in this area. The ring has a size of 1 member, 2 member, 3 member, 4 member, and 5 member. So 5-member rings are generally stable. In case you remember, in case of organic chemistry, I know you should you have learned that bare angle strain theory. In case of bare angle strain theory, we knew that the 5-member rings and the 6-member rings are generally stable. So you should see what happens during the chelation. So as the chelation occurs, this has become a cycle. So now here, see here, in case of K for FeCN6, what happens? There is a bond between iron and cyanide. So there is a bond between iron and cyanide. We know that the bonds are not like rigid axis; they are spring-like. So whenever some amount of energy, that is the ultraviolet energy or the infrared energy or the thermal energy or the etc., some amount of energy comes here, the vibration of the molecule, cyanide atom or molecule take place. So due to the vibration, the entropy increases, randomness increases, and the stability decreases because the potential energy increases. But in case of chelates, we know that there is a cycle here. So a higher amount of energy is needed to vibrate the whole ring. You should see, you cannot vibrate any particular part of the ring. So you should vibrate the whole ring. So that needs a higher amount of energy. So you cannot vibrate the whole ring. So chelates are highly stable because during the chelation, the vibration decreases, the randomness decreases, the potential energy decreases, and the stability increases. So the chelates generally does not undergo any kind of addition or elimination reactions in the normal condition. Although in case of this chelate, if you do the substitution in the acidic medium, then it can be broken because the lone pair of nitrogen will attract the hydrogen, so that the lone pair will not be available for the donation, so that the chelate should be unstable in nature. Ambidentate ligand. Ambidentate ligand is another classification. Question comes from here. Ambidentate ligands 2 donor atoms, but certain cases can be coordinated through only 1 donor atom. You should see the structure. See, the classical example is a cyanide, nitro group, and SCN, thiocyanide. You should see here, cobalt is present here, cyanide. So in case of cyanide, there are 2 donor atoms. You should see one negative charge is present on the carbon atom, and a lone pair is present on the nitrogen atom. So cyanide can coordinate through both their donor sites. Cyanide can coordinate through both their donor sites, but this is not possible because in case of if it acts as a bidentate ligand, the chelate ring that is produced, the chelate that is produced has a three-membered size, three-membered ring. So three-membered ring are generally not stable according to the Bayer-Engel strain theory. You know that in case of organic chemistry in class 11 we have learned that the Bayer-Engel strain theory says us that any deviation from the normal carbon-carbon bond angle should cause an angle strain. So the three-membered rings are generally not stable. So you should see cyanide cannot act as a bidentate ligand. So it acts as an ambidentate ligand. That means it has two donor sites, but in a specific case can be coordinated through only one donor site. Now see here, cobalt is here present, cyanide is here. So the linkage is done by carbon atom. Here is NC. The linkage is done by nitrogen atom. So there is a carbon atom linkage. There is a nitrogen atom linkage. Now you see, if the linkage is done by the carbon atom, then it is known as cyano. If the linkage is done by the nitrogen atom, then it is known as isocyano. It is done by cyano. It is done by cyano. It is isocyano. Now you see that there are generally many kind of ambidentate ligands are present, but in case of your syllabus, you should remember these three ambidentate ligands. I think this is enough. Nitro, cyano, and thiocyano. If the linkage is done by the nitrogen atom, it is known as nitro. Oxygen atom, it is known as nitrito. In case of cyanide, in the linkage is done by carbon atom, then it is known as cyano. It is done by nitrogen atom, that is known as isocyano. If it is done by the sulfur, that is thiocyano. If it's done by the nitrogen, that is known as the isothiocyanate. Now you see, always remember, we should come to that. Always remember, these three ambidentate ligands always show linkage isomers. This is a very important question which will come. Now you see here another classical example or classification which is known as the pi acid ligands. This is very important. Now you should see here, there is a metal atom, there is a ligand. Metal has two orbitals which are both of them are empty. In case of ligands, one is filled, another is empty. So the filled is known as, this is the sigma orbital, okay? Sigma BMO. BMO stands for bonding molecular orbital. BMO stands for bonding molecular orbital. And this is pi ABMO, pi antibonding molecular orbital. This is also known as the HOMO, or this is known as the LUMO. HOMO means for highest occupied molecular orbital, lowest unoccupied molecular orbital. You should see the ligand, which is here. I'm saying again, in case of ligand, you should forget HOMO and LUMO. These are not necessary. Of course, you should see this. This ligand has two lobes or orbitals. They are molecular orbitals, of course. One is sigma BMO, that is sigma bonding molecular orbital. Another is pi ABMO, pi antibonding molecular orbital. Pi ABMO, that is the pi antibonding molecular orbital. In case of metal, one is sigma BMO and another is pi ABMO. Here both of them are empty. Here one is filled, another is empty. Now you should see, at first the ligand gives the electron to the metal atom and forms a sigma bond. There is sigma to sigma transfer, so it is sigma bond. Sigma to sigma transfer, it is sigma bond. This ligand donates electron to the metal atom. This forms a sigma bond. Fine. Now you should see, metals are generally electropositive in nature, so they will not generally accept electrons. So the metal does what? It transfers the whole electron to the pi orbital and then gives back to the ligand. This is a pi bond because pi to pi transfer has been done. So ligand to metal sigma bond is formed. Ligand to metal sigma bond is formed. Metal to ligand pi bond is formed. This kind of sigma and pi bond is simultaneously formed. That is known as the synergic bond. You should remember this is synergic bond. I'm saying again, what is synergic bond? The ligands first donate the electron to the metal atom, and the metals are generally electropositive, so he is not wanting to have your electron, he is wanting to release the electron. But so he does what? it transfers the electron to the pi orbital, pi ABMO, and then it transfers the whole electron to the ligand. Now what happens? Two bonds are formed. One is sigma to sigma transfer is called sigma bond. Pi to pi transfer is known as pi bond. This is known as synergic bond. And always remember, the pi to pi bond, the pi to pi transfer is known as the back bond also. This is known as the back bond also. This is very important. Okay. Stronger the back bonding, stronger is the complex. You should know that. Stronger the back bonding, stronger the bond between the ligand and the metal. So these type of elements, this type of ligands such as cyanide and carbon monoxide are very, very strong. So they can form very strong coordinate bonds. So I can give you one example. In case of what happens when someone takes or inhales carbon monoxide or cyanide. So what happens? There is a porphyrin ring in hemoglobin. Okay, so this porphyrin ring has a cavity in which the iron can sit. Iron is first in the low spin, high spin condition, but whenever oxygen is binded with the iron atom, so it goes to the low spin complex, low spin state. Now what happens if cyanide or carbon monoxide is taken or inhaled, or by any means it is intake in the body? What happens? Cyanide replaces the oxygen, or the carbon monoxide replaces the oxygen and forms a stronger bond with the iron atom. Now oxygen transfer in the body hampers, and moreover these kind of compounds such as hemoglobin or cytochrome C, cytochrome P450, they also act as the electron shuttle in the body. So what happens whenever the oxygen is eliminated and the carbon monoxide is taken their place, then the electron transfer in the body disrupts and collapse happens. So so you can also reverse this position. You can, if you give sodium nitrate nitrate solution in a certain quantity in the intravenous condition, so this can produce met hemoglobin or newly formed hemoglobin, which can conduct the oxygen in the body, and the rest of the contaminated hemoglobin should be eliminated from your body in a certain process. Now we should go the next, that is the stability of an complex. You should see this is EAN, effective atomic number. Effective atomic number, generally this is an old process. Is also nowadays also it is in the process. EAN is found in such a way. Now see, the formula is like that: atomic number minus oxidation state plus total number of electrons donated by the ligands. Atomic number minus oxidation state plus total number of electrons donated by the ligands. Now you see, in K4FeCN6, potassium ferrocyanide, K4FeCN6. Now you see what happens. Atomic number, that is 26, minus, you should find out the oxidation state. Potassium has +1 oxidation state, 4 potassium, so into 4 plus I have taken, let us take the oxidation state of iron to be X, plus cyanide has a -1 oxidation state, so so 6 cyanide atoms are present into 6 minus 6, so that is equals to overall the molecule is, you are seeing that it is electrically neutral, so it is equals to 0, so X is equals to +2, so the oxidation number of iron is it has become +2. So now you see, um, mm, okay, according to the formula, atomic number, that is 26, minus oxidation number, that is +2, and total number of electrons, that is 6 into 2 is equals to 12. Now if you do the calculation, you will find out that is 36. Krypton, 36 is the atomic number of krypton, you know. So by the rules, this is by the rules, what happens when the effective atomic number of effective atomic number of some complex compound becomes equal to the noble gas electronic core configuration, the complex becomes stable. So potassium ferrocyanide has a certain amount of stability. We can see another example of this one is a very good example: COEN whole 3 Cl3. Now we should find out the oxidation state, that is equals to +3, because X is the oxidation state plus Yeah, and ethylene is a neutral ligand. It has a zero oxidation state, so it is 0 into 3 ethylene diamides are present, plus one chlorine atom has minus 1 oxidation state into 3. That is equals to the molecule is overall electrically neutral. So this has become 0. X is equals to plus 3. So the oxidation number becomes plus 3. Now you should calculate the EAN. 27 is the atomic number, minus oxidation state is plus 3 plus total number of electrons donated by the ligands. You should see here, this is ethylene diamine, so it is a bidentate ligand. You should see, so number of bidentate ligands present is 3. So one bidentate ligand has 2 donor sites, that's why it will donate 4 electrons. One bidentate ligand will donate 4 electrons, so 3 bidentate ligands donates 12 electrons. Now this becomes 36, that is, it is also stable. So today we finish here. If you like the video, then you can share, or share to your friends, that everyone gets some information. I'm trying my level best to give you the informations, and we should do some live classes also. And please, if you like the video, please share. And if you want to know anything, you should comment in my comment box, and I will definitely give the answers. Okay, thank you.